I will then introduce Mr. William Moses from MIT, who will be talking about enzyme.
Thanks, everyone. I'm going to be presenting my talk here, Post-Optimization Automatic Differentiation by Synthesizing LLVM. The first part of the work that I'm going to be presenting is by myself and Valentin Cherevy, and then the subsequent piece on sort of like CUDA and additional optimizations in the world of automatic differentiation is joint work between a large group of people, and hopefully will be accepted in a submission that we're preparing for Friday. So to begin, differentiation is rather important for algorithms in a variety of domains, specifically in the machine learning realm. Backpropagation inside of neural network training, Bayesian inference, and uncertainty quantification all rely on automatic differentiation to be able to go ahead and compute the underlying results of these algorithms. In the scientific computing domain, this is quite common in the worlds of modeling and simulation and the like. In all of these specific areas, you can imagine trying to go ahead and manually write derivatives by hand, but especially for large code bases, or if you have dynamically generated programs, manually writing all of these derivative functions quickly becomes intractable, in addition to the fact that it may not be the most high-performant way to do it. As a consequence, the community has developed a variety of tools to be able to go ahead and take an existing program and generate a function that computes the derivative of that automatically. Typically, these have one of three different approaches. The first approach is to create a new differentiable domain-specific language. And in that, you create this new language that's explicitly designed to be differentiated. This works, but requires, if you have an existing code base, rewriting your entire code to be inside of this new DSL. And of course, the DSL must support every type of operation in your original code that you're hoping to be able to do. If whatever your original program is matches quite well with the abstractions inside of your DSL. So for instance, if you had like a large set of matrix multiplies and your DSL had these highly optimized matrix multiply operations, this would work quite well. But if you have something dynamic inside of, say, your physics code, unless it has, say, high-level operators that are exactly designed to match those physics operators, the sort of mismatch between abstractions ends up quite hurting performance in certain cases, and thus differentiable DSL really depends on exactly what you're doing. The second main approach is known as operator overloading. Examples of this include adept for C++ and JAX for Python. In essence, they attempt to provide a differentiable version of existing language contracts. So for instance, inside of C++, in adept, there might exist the double type, for example, and if you wanted to compute an operation with that double type and differentiate it, you would replace all uses of double with this differentiable a double, and then it would allow adept to track all of the uses of your code and then compute the derivative as a consequence. Similarly, inside of JAX, it replaces not quite standard, but this common library NumPy, a numpy.sum with a jax.sum. Of course, all of these additional either libraries or operator overload template parameters may require rewriting the code to, first of all, use these new variants of the standard utilities. But in addition, for instance, in JAX, it may not support all of the existing NumPy operators, or for instance, in adept, it might not support a sign or some specific variant of a double, and thus you would have to rewrite your code to make sure to use the subset of the language supported by the operator overloading tool. Moreover, and this is especial for adept, these types of tools tend to be dynamic, which says that rather than ahead of time computing what this derivative function may be, when you compute the forward pass, originally it would track for every instruction what you're actually executing into a stack that for the reverse pass later is interpreted, and this is not good for performance. The third approach is known as source rewriting, in which you have some tool that takes in the source code of whatever program that you want to differentiate. It'll statically analyze it and then produce a new gradient in that original source language. Existing approaches aren't great, and they tend to have to re-implement parsing in the semantics of a given language, and thus as a consequence, similarly have to rely on using a subset of the language currently supported by the tool. Moreover, it also requires all of the code that you want to differentiate to be available ahead of time, in that if you wanted to, say, use a dynamically generated piece of code, you need to dynamically generate it, then push that into the tool. As a consequence of this, it makes it rather difficult to use with external libraries, since all of the external library code may not be available to the tool when you want to go ahead and differentiate it. Generally, all of these existing tools tend to follow the same pattern, though, in which you have your original function in any choice of source language, be it C++ to Rust. Then you differentiate it, and it'll use some new code in that original language. Again, the same C++, Julia, or Rust. And then you do the traditional compilation pipeline, which typically involves lowering to some intermediate representation for which you can do optimizations and then eventually create your final executable. Let's look at how this traditional pipeline works in practice for a sample code. So here I have a program that first defines a magnitude function that takes in a vector and in O of n time returns the magnitude of the vector. And then we can use this to to normalize a particular vector. So we have this input vector and an output vector. And inside of the for loop, we say the output vector equals the input vector divided by the magnitude. And the way that it's written, it runs in O of n squared time, which works, but it's not great. And one thing that you might want to do, for instance, is to move that call to the magnitude function outside of the loop, which is highly beneficial for the standpoint that then it reduces the runtime from O of n squared down to O of n. So if we look at how we might want to go ahead and differentiate that, if we were to first do that optimization that I mentioned, where we move it outside the loop and reducing the runtime down to O of n time, and then differentiate it, this corresponding reverse pass shown on the right here would mirror what the original code is like, and as a consequence have the gradient of the magnitude function outside of the loop at the very bottom. And this results in the gradient of this running in O of n time as well. However, let's imagine what happened if we did it with a traditional pipeline that all of these existing tools have to do, where they have to run AD prior to any optimization. So first, we have our original code, the O of n squared one, and we run AD on it. And similarly, this mirror of the original code has the gradient of the magnitude function inside the loop, meaning that the reverse pass alone takes O of n squared time to compute. Now we can imagine trying to apply that previous optimization to the gradient magnitude function, but unfortunately we can't move it outside of the loop. And the reason for this is that the gradient magnitude function uses a variable defined in the loop, this dres, which then prevents it from being loop invariant code motion. And then as a consequence, we're stuck with the O of n squared reverse pass. So the big thing though to take away from this is that differentiating after optimization can create asymptotically faster gradients. So that's what Enzyme's goal is to be able to do. So specifically by moving differentiation down to the LLVM level, we're able to work on already optimized code, and as a consequence, get those benefits of being able to apply optimization first, and then do automatic differentiation. So one might then ask why we specifically chose to use LLVM as opposed to any other optimization infrastructure. So LLVM is itself a generic low-level infrastructure with a variety of front ends. And you can sort of think of it as being a cross-platform assembly in some sense, with a little bit of nicer semantics that are well-defined and thus slightly easier to go ahead and differentiate. Moreover, in addition to having a variety of front ends, it similarly has a variety of backends. So we can imagine writing differentiation once effectively and have it apply to all of these both front ends and back ends at the same time, which is really nice. Additionally, inside of the LLVM infrastructure itself, it contains a variety of both optimization passes and analyses that we'll see are actually quite beneficial to be able to leverage over the course of differentiation itself. So let's look at how we might go ahead and specifically optimize and differentiate a sample program. So on the left, I have this ReLU3 program, which says I want to compute, excuse me, the derivative of, x cubed if x is greater than 0. The actual way we would instantiate the derivative is shown on the bottom, where we call this magic function enzyme autodiff. We pass to it first the function we want to differentiate, followed by any of the corresponding arguments. On the top left, we have the call to this function we want to differentiate, ReLU3. On the bottom left, we have the way we would go ahead and differentiate it. And on the right, we have the corresponding LLVM. So looking at the LLVM, we first have a branch to see if x is greater than 0. If so, we'll go compute pow on the left, and if not, we'll go and return 0. Specifically inside of LLVM, we have these basic blocks, which can be thought of as containers of instructions, where the instructions in this case are highlighted as the things we might want to individually differentiate. So the first thing that Enzyme does is it goes ahead and it analyzes for every instruction and value inside of the original code, what are the active instructions? In other words, what are all of the instructions and values that can impact the resultant gradient or derivative computation? In this case, the resultant values that could matter are first the argument x, the call to the pow instruction, the phi node that combines these together, and finally the return. From there, for all of the values that we deduced were active, we're going to go ahead and allocate in 0 shadow memory to store the current computation of the gradient for those values. From there, we then go for every individual active instruction and compute the corresponding adjoint for these. In this case, the adjoint is the propagation that says effectively how do we propagate the derivative of the output up to its inputs. So specifically, if we look on the left here, we have the instruction pow of our x cubed. And then the corresponding adjoint for this is to propagate 3 times x squared up to x, for instance, as the derivative. Doing a little bit more optimization on that code we generated earlier, we get something that looks quite nice. And at the very bottom, we see it's essentially the optimal gradient that one would go ahead and handwrite for this case. There are, of course, challenges of being able to apply automatic differentiation at a low level. And this is not even specific to LLVM. So here I have a, for instance, mem copy inside of C, where I copy 8 bytes from some source pointer to a destination. And if the data actually it represents doubles, then the corresponding reverse passes to do 1 8-byte floating point add is shown on the left. However, if the data actually represents floats, then the corresponding reverse passes to do 2 4-byte floating points adds, as is shown on the right. And mixing these up means you'll get a completely incorrect result. So it's important to be able to identify exactly what the underlying type of your data is. The way we specifically resolve this is we introduce a new interprocedural data flow analysis that attempts to go and detect for every single value what the underlying types of these are. So this starts off by assigning to every value a set, or specifically a tree of memory offsets to whatever corresponding type underlies that. After initializing all of the information we have at first, we then perform a series of fixed point updates where we say for every type of instruction, what's the propagation rule that says how the resultant types can be computed from the input types, and so on. As an example of this type tree, we have the struct on the left, which contains first inside of it a double, then a pointer to an integer. And if we want to consider a pointer to that type, we would have the type tree shown on the right, in which first we have a pointer at byte offset 0. And then inside of that, we have the previously mentioned struct, where that struct at byte offset 0 contains the double, and then at byte offset 8 contains a pointer. And of course, that pointer points to an integer. Additional things that are often quite relevant is one might want to specify custom forward or reverse passes of functions. And this is useful for a variety of reasons. First of all, you may have some algebraic information that says you can compute a faster derivative, say because you know the derivative of this particular quantum operator must always be 0, for instance. So that can be augmented into the system by attaching specific pieces of metadata. Moreover, this also makes it a little bit easier to integrate into existing systems. The second big question is how Enzyme is able to integrate into tools that either use multiple source files or, for instance, that have external library calls. And Enzyme does so by leveraging existing tools in LLVM, specifically link time optimization, which says, I want you to keep around the LLVM for all of your functions, and then at link time, run some additional optimizations. And as long as we run with link time optimization and then run Enzyme at link time, this ensures that we have all of the source or LLVM available for us to be able to differentiate. Moreover, these fat libraries effectively include both LLVM and the actual binary itself. So if we need to look at the definition of an individual function, then we have that accessible. From here, we did a series of benchmarks. So we took Microsoft's AD Bench suite, which is specific to machine learning, and a couple of others of technical interest, and attempted to evaluate how Enzyme compared. So first, the Enzyme pipeline is to first run optimization, then run Enzyme automatic differentiation, then a subsequent optimization pipeline. To best mirror how other automatic differentiation tools have to work, we then had a reference pipeline that first ran the exact same Enzyme automatic differentiation, then 2 rounds of post-processing optimization. We then took the 2 fastest automatic differentiation tools from Microsoft Suite. That's Topinod, which is a source rewriting tool, which of course has to have run before any optimizations, and Adept, which is an operator overloading tool, which again has to run prior to any optimizations. From here, we can look at how the results came out. So the first thing to consider is the difference between Enzyme and the reference pipeline, which is just as a scientific study to evaluate how much this pre-processing optimization really matters for differentiation.
It's again freeze the slides.
It's again frozen. Okay, one more moment. Oh, Zoom. Thank you so much. Okay, can you see this now? Slide 25, the bar chart.
Yes.
Yes.
Excellent. Okay, so first, the thing to evaluate is how much those optimizations really matter. So we can do so by looking at the difference between enzyme and the reference pipeline. And we see that for the majority of test cases, enzyme does substantially better. And in fact, on average is 4.2 times faster. Diving in a little bit deeper, we see that most of the benchmarks see a fairly substantial speedup, but two of them at the end, the FFT test and the Brussels rater, don't see much of a speedup at all. And the reason for this is that both of these two were already highly optimized. So running any LVM optimizations on it didn't make a difference unless we see them as effectively equal. However, the other larger machine learning benchmarks like LSTM and bundle analysis have quite a rather large speedup there. The next thing to look at specifically is to look at how enzyme compares with a tool like Topinot, the source rewriting tool. So first, if we again look at the LSTM and bundle analysis tools, we see that the reference pipeline for enzyme and Topinot are fairly similar. So we can fairly conclude that a lot of the performance benefit that enzyme has over that tool comes from the ability to run optimizations first. Of course, those aren't equal across the board. And the reason for this is there's differing implementations of derivatives and moreover how caching works between these two tools. So for instance, we can see a gap in the generalized matrix multiply between these and others. Similarly, Adept has additional caveats for its implementation. Specifically, unlike both Topinot and Enzyme, it has to dynamically store all of the instructions that are evaluated in the forward pass, and then in the reverse pass, interpret what those are to generate the corresponding derivative, which as a consequence is an additional slowdown, usually compared to these other tools. From here, I'm going to talk a little bit about some ongoing work, which is in submission about how enzyme goes to differentiate both parallel code as well as CUDA code. And it turns out that differentiating parallel code comes with some additional caveats and additional complications. So specifically, if we consider the code on the left, which is effectively sets an array or 10 values inside of the array to be some individual value passed in. Since all of these iterations are independent, we can in theory parallelize this with a parallel for. In doing so, we have a read race on the variable val, which of course doesn't complicate this or create any additional difficulties since it's perfectly legal and deterministic to read in parallel from the same location, provided it's not being modified. Unfortunately, however, for the reverse pass, this presents difficulties because the read races and the forward pass become a write race for the reverse pass. So the corresponding code on the right-hand side illustrates that we're trying to update the gradient of value in parallel in the corresponding reverse pass with this parallel accumulate, which by virtue of being the parallel for is a race and then can lead to non-deterministic or completely incorrect behavior and requires special handling as a result, which I'd be happy to talk about offline. A couple of specific things that we do in this case is we go ahead and detect one of three different cases that can happen for this memory. So the first case is that the memory itself is thread local, and we can simply do a non-atomic load and store for the update, and that's perfectly acceptable. The second scenario is that it's the exact same memory location across all threads. In this case, for instance, in the middle, we have a global variable y that everyone is updating in parallel. That's what the little device function is in the CUDA land. In doing so, we can just do a parallel reduction across all the values that we want to add into it, and that should be sufficient. And then the final case, which is always legal as a potential fallback, is we can do an atomic increment to propagate the corresponding derivative value inside of that, which is legal in cases where it's either thread local or the same memory location, but perhaps not as performant. A couple of other caveats that come into play, especially when doing CUDA code as opposed to just generic parallel code, is that enzyme may need to cache particular values from the forward pass for use in a later reverse pass computation. So for instance, if you were differentiating x squared, for instance, the corresponding derivative of this is 2 times x. So to update the corresponding reverse pass, you need that original version of x to be available. So on the right-hand side part of the code, we have this generic compute function that computes a value temp, and then we use it in a way where we square it, which means that the corresponding reverse pass, as shown below, must cache the value of that compute from the forward pass to be able to compute 2 times whatever that iteration's version of that value was. Generically, yep.
Sorry to interrupt. Which slide are you at?
28.
Okay, so I see 26. Maybe you can do your magic.
One more moment. Once again, Zoom is being slightly unhappy. Okay, can you see slide 28?
Yes.
Okay, excellent. So in essence here, we have this value temp, which is overwritten every single iteration, and thus isn't available for the reverse pass. And since we need the original value of temp from that iteration to be able to compute 2 times that value to compute the derivative of temp squared, Enzyme has to, or any AD tool generally, needs to cache that value for later use in the reverse pass. In particular, when such a value needs caching, Enzyme will go ahead and allocate memory, which in the case of Kuna is done via a malloc of global memory inside of the kernel, which is unfortunate because global memory is substantially slower than both shared memory and registers. And in addition to just generically being slower, may overwhelm the total amount of GPU heap memory that's available. So it's highly desirable to do a number of optimizations that try to reduce the total amount of cache. In particular, on a variety of DOE proxy benchmarks, we evaluated to explicitly explore their potential for being automatically differentiated of the in a CUDA context. First, we evaluate their forward pass, and then a variety of versions of optimizations that try to reduce the previous issues alluded to. So first of all, if we go ahead and try to take the gradient of these codes in a similar way that one of the existing AG tools like Tapanod or Deft would do, which is to say no optimization, even the standard ones, prior to running AD, it instantly out of memories just because of the amount of code that needs to be cached for the corresponding reverse pass. If we then go ahead and apply the standard thing that Enzyme does, which is running some standard, say, O2 as pre-processing optimizations, we can succeed at running on the GPU without running out of memory, which is fantastic, but there's still a relatively sizable difference between the actual runtime of that, which for X's bench is 20 seconds versus 1 second for the original primal code, and greater than 540 seconds versus 2 seconds for RS bench. So it runs, but not substantially great. We then implemented a variety of cache-specific optimizations, both generally for LLVM as well as inside Enzyme in particular, as can be derived in an AD context. And that's able to substantially reduce the runtime of these programs. In this case, from once for XS bench, where it was originally 1 second for the forward pass, 20 seconds without these optimizations for both the forward pass and reverse pass combined, down to now about 5 seconds for both the forward pass and reverse pass combined. Similarly, for RS bench, we've reduced 2 seconds down to 8 seconds. So overall, about like a 4 to 5x slowdown to be able to do both the forward and the gradient, which is substantially better. A couple of cute things that we also have here as additional results are, so we implemented versions of Enzyme for both PyTorch and TensorFlow that allow you to import existing foreign code, such as in this case, this test.c and the function f within it inside of your ML framework. And the goal of this being that your ML researcher can now just import arbitrary existing foreign code without having to do the substantial rewriting work to be able to go ahead and apply it. Overall, specifically, Enzyme can be thought of as a tool for being able to perform reverse mode automatic differentiation of statically analyzable LLVM IR. And specifically, working at the LLVM level provides 2 key benefits, the first of which is to be able to differentiate code in a variety of potential front-end languages, as well as the ability to do AD prior to optimization, which, as we demonstrated alone, provides a 4.2x speedup, which is fairly substantial. As a consequence, Enzyme's able to achieve state-of-the-art performance when compared with existing tools. Enzyme's also able to go ahead and differentiate GPU kernels with some extra interesting things for the sake of being able to do optimizations on GPU codes. And if you're interested in that, talk to me after, or come to the GTC talk in about a week for some more details on that. Enzyme itself is open source, and we finally allow mechanisms for people to import foreign code without having to do this rewriting. Thank you so much. Any questions?
Thank you, Billy. Questions, anyone? I have one question. I was trying to unmute myself. So in the work that you mentioned on the GPU kernels, so in principle, the fact that the scheduling of the function needs to be probably differentiated so that it fits the newly generated gradient function. Is that have you thought of a generic way to do it? So the problem is that you will have function f that executes on the GPU with some scheduling that comes from the compute kernel or whatever. But then the theory says that if you have a gradient, you will have 4 times, at most 4 times more operations to compute the gradient itself. So presumably the old scheduler for that function is not efficient for the gradient itself.
So that overhead, when we're doing various amounts of benchmarking, doesn't usually come from the overhead from computation. Certainly a fair amount comes from the fact that you're at least doubling the amount of computation potential to be able to compute the corresponding reverse pass. But we also found that a lot of additional overhead comes from some rather GPU specific pieces for both memory and otherwise. So as we illustrated, you may need some values from the forward pass to be recomputed for the corresponding reverse pass. And any use of memory is inherently slow. And that's part of why we're adding a lot of optimizations to reduce that, and hopefully can even further reduce that, as previously alluded to. The second reason even isn't a memory specific one, but something we also found is that by increasing the amount of things that need to be kept around potentially for the reverse pass, even if they don't go through memory, means that we might have more registers. And the fact that we're increasing the register pressure itself means that the GPU scheduling might end up being slightly slower, or even worse, having to spill registers that then falls back to having to do some amount of allocation of memory. So then a lot of the additional optimizations that we're hopefully going to be exploring, which we actually found a minor LLVM bug of like a mismatch of shouldn't run GVN in a different way in contrast to inst combine, is being able to do specific like instruction scheduling to be able to move these registers to where they're closely used, as well as being a lot more aggressive in terms of the do you want to cache this versus do you want to recompute this heuristic, to say, especially for CUDA kernels, almost always you want to explicitly recompute that because of the vast amount of slowness that comes from any amount of use of memory and even registers, as mentioned earlier.
Okay, thank you. More questions? Okay, if there are none, thanks again.